Thanks, and I realize that this is going to be trying for lunch reasons, but I'm trying to go quickly. And I think the good news is that I am nowhere near as sophisticated as the various people who have worked on the things that were presented before this. So the attention, perhaps that's good news for getting to lunch a little quicker. Okay, so my motivation is really to, I'm sort of a one-trick pony. I think about tensor networks. I view everything in terms of that. If I can't see a good picture, I give up and I move on. And so I have a picture, and I want to sort of share that picture, and then also in the process tell you how that picture tells you something about Kitaev's strong coin flipping bound. So this is work with Thomas. And so I had all kinds of plans to put fancy slide here, but then I decided I had half an hour, and I was going to embarrass unknown people on the internet with pictures of birthday parties that I didn't know. So it didn't. But anyway, so the strong coin flipping, which we've heard about already a bunch of times, is me and Dorit want to flip a coin, and we really want it to be fair. All right, we don't quite know what outcome each of us, we're sort of suspicious. Maybe each of us wants some outcome that we don't know why, but we want it to be fair. And so that's strong coin flipping as opposed to weak coin flipping. What does Kitaev's result say? It says that you can't do this perfectly, right? You can only do this. So if we have a strategy where if we both played honestly, we could actually flip a coin fairly, then at least one of us can cheat while the other one is doing fairly, so that we can bias the coin in a particular direction up to about square root of 2, to exactly square root of 2 over 2. And this was proved originally by Kitaev, and then a nice different proof was given by Gutowski and Watrous. And the ideas here are sort of really mimicking or sort of motivated by that stuff. And this bound is, as we've heard multiple times, this bound is tight. We can actually achieve these things. All right, so okay, so I'm going to tell you about a different game, and the word dual is used, but it's not the dual as an SDP dual. And it's a game of which I'm going to show the kind of bias that Kitaev's coin flipping is the same result as Kitaev's coin flipping in terms of the bias. And then later on, I'm going to show you why we can view coin flipping as a duality game. So the duality game is rather simple, which is Alice is constrained to play from some convex set of positive matrices. Bob gets to play from the dual set, meaning the set of positive matrices for which this should say somewhere in here it should have been that the trace of BA is less than or equal to 1 for all of Alice's choices. Right? And the outcome of the game is when Alice plays A and Bob plays B, the outcome is the trace of it, AB. Okay. And suppose we have the situation where we have what we want is an honest protocol, which is that a play by Alice and a play by Bob, for which the outcome is a half. Right? Let's say that's the probability of coming up heads. Right? Okay, so this is our setup. Suppose we have this. Well, then the result is cheating can happen. Right? What do we mean by that? We mean that if Alice plays honestly, Bob can find a cheating strategy, or if Bob plays honestly, Alice can find a cheating strategy for which at least one of these is bigger than the square root of 2 over 2. And in fact, what it actually says is that the product is greater than or equal to half, which then allows you to show that at least one of these is bigger than square root of 2 over 2. And so let me show you the picture of how this proof works, right? Which is honest to God proof. So the blue is the set of Alice's possible matrices. Right? And Alice has this strategy, right, which her honest strategy, which sits there. And what do we know about Bob's honest strategy, right? Which is that the trace of their product is going to be a half, which I'm depicting by a projection. Okay, so picture it as though these are vectors and this is an inner product. This is our starting setup. Right? So now we ask, how can Alice cheat? Well, Alice can cheat by trying to make that inner product bigger, right? And so here we see where she can go. She could go there, right? And if Alice cheats and Bob stays the same, okay, then there's some cheating probability that's at least a half, which we'll call P. Okay? So this would be this is telling us that this number is P. Okay?
Where's the origin of the diagram?
Oh, this was supposed to be the origin. Okay. Okay. So, all right. Now we've designed Alice's cheating strategy. All right. So now, let's just notice something here, right? The biggest that Alice's cheating strategy could get was P, right? Now, Bob has in his repertoire anything for which as long as his strategy on the whole set is less than or equal to 1 is okay. So actually, Bob has a cheating strategy he has a strategy that he could play that's a scaled version of B0 that makes this optimal point, instead of having a value P, to have the optimal point have a value 1. Okay. So that's what I'm trying to depict here. So I've drawn a parallel line because I would want to put it right on top of this one, right? But his calibration of what the values are has changed because he's scaled up. So his value is 1, which means now, since his value, we've just scaled these things, we know what his value is on an honest, if he was to play this strategy versus Alice's honest strategy, he would move from 1/2 to 1/2p.
Wait, sorry, I missed something. It seems
Possibly.
like they're both trying to increase the number by.
Yeah, that's what strong coin flipping is. Right, so you don't want either. We don't know who wants heads,
Oh, I see.
but we want to guard against the possibility that one or the other of us can influence it towards heads. Okay, so what do we got here? So we've shown that there's a cheating strategy for Bob that achieves 1/2p, a cheating strategy for Alice that achieves p. Their product is 1/2, right? And that allows us to conclude what we wanted, which was at least one of them was bigger than square root 2/2.
Sorry, can you repeat the argument for the B?
For the B? Yes, I can. So this is where we stood, right? We found the optimal cheating strategy for Alice, right? And the optimal cheating strategy for Alice produced a value of P. Well, in Bob's repertoire is any scaled version of B0 as long as on the whole convex set, their value is less than or equal to 1. Okay? Well, if the biggest value can be P, then I can take in the repertoire instead of B0 a scaled version of B0. That's in my dual thing. And what scaled version can I use? I can use 1/p times B0 because that'll give my value to be 1, which is the biggest that I'm allowed it to be. Okay? And then if I do that and I figure out what happened, this is just a scaled version of the old one, so it just scales my value against A0, and it scaled it from 1/2 to 1/2. Okay. Yeah, we're done. We can go to lunch. Okay, so the rest of this talk is to convince you that, in fact, what Alice and Bob are doing are playing this kind of duality game. So what do we want out of it? We want to say that Alice is playing from some convex set containing 0, positive operators, and Bob is playing in a dual.
In coin flipping, you mean?
In coin flipping. What did I say?
You didn't say.
Oh, okay. That's sort of okay. Sorry. In coin flipping, in the coin flipping, that's what's going on. Okay. So what that is equivalent to saying is an understanding of this picture. Okay. So my motivation now is to have you understand this picture, which there's no reason you should understand right at the moment, just to give you a sense of where we're going. Okay, so to do that, I have to tell you about tensors and tensor networks, which I'm going to do pretty quickly. So just, by the way, can you just raise your hand if you know tensor networks marginally well? Okay, all right, thanks. Okay, so I'll tell you it from my point of view, how I think of it, and there are some conjugates and various things that don't show up, which is fine. You can ask me about it, and I'll say, don't worry about them. But anyway, so what is a tensor? A tensor for me is a picture like this, right? And I have to tell you how to understand this picture. So it's a picture with a node and a bunch of edges coming out of it, right? And each edge, I'm going to have some rules for how this picture. Each edge can be labeled one of d different things. Right? It's called the set 0 through d minus 1. And this M, this node, comes with the property that if I label every edge by some of these, any of these labels, outspits a number. Right? So I've just given an example where instead of using numbers, I colored them different colors, but imagine the yellow was 0 and the green was 1, and et cetera. Right? So for any labeling of these edges, another number comes out. So it's just an array of numbers, if you'd like. Okay. But I want to think of this array of numbers in a bunch of different ways. Right? And it's going to be important that I think about them always in a bunch of different ways so I can move from one way to another, visually not a problem. So to do so, first I'm going to start with a Hilbert space, just a finite dimensional Hilbert space. It's D with CD, D-dimensional Hilbert space, and I'm going to pick a standard basis for it, which is no coincidence that I'm sort of corresponding them to the labels. Right? And so then, one way I can interpret my M now is a vector in a tensor product copy of H. How many copies of H? One for each edge. Okay, so in this case, there are 5 edges. So I can view M as a vector in H tensored together 5 times. And how do I view it? I'm going to just tell you its coefficients. The M is going to tell me its coefficients on a basis. What's the basis? To tell you the coefficient for the I1 through I5 basis element, I'm going to spit out the number associated with labeling the edges I1 through I5. And what is hidden here is a correspondence between there's a choice of these 5 and a choice of edges, and I have one copy of H assigned to each edge. Okay? So I arbitrarily say this is the second copy of H, third, fourth, and fifth, and so now I1, I2, I3, I4, I5. Okay, so whenever I see a picture, associated to this picture is a vector. But that's not all. There's also going to be another association. I'm going to freely move from those, and that's to interpret this tensor not as a vector, but as a linear map. And not as one linear map, but as a bunch of linear maps. So let me give you an example of one of those linear maps. I can view it as a linear map from, let's say, these 3 copies of H, so tensor H 3 times, to another Hilbert space, which is the tensor copy of H 2 times. And now, to tell you a linear map, I have to tell you what the map is. Right? And so I'm going to define it on a basis for this Hilbert space. Right? So to do so, I have to tell you so if I've labeled this I1, I2, I3, right? Oh, did I do it? Yeah. I've done, imagine there's an I3 here. Put this I3 over there. Okay. All right. Okay. So I imagine I've labeled it I1, I2, I3. And I want to say, I'm going to tell you how I send that basis element. I'm going to send it to a sum over I4s and I5s. And I tell you what the coefficient in front of each of the I4s and I5s is. Well, with I1, I2, I3 in the bag, labeling the first guys, and I4 and 5 on this side, I've labeled everybody. So M is now a number again. There's a number associated to it because I've labeled all the free edges. And that's the number I put in front here. Now, I could have done that with any combination of edges, right? I could have put some of the edges in the front and some of the edges in the back, and sort of I have all this different classes of maps. And this is basically the point of tensor networks, is that a single diagram has all kinds of different interpretations as linear maps going in different directions. So we'll see some examples. So now I want to tell you how to take these. So I've told you what this means, right? This is an array of numbers. I can think of it as a map or as a vector. I've told you what that means. Now I'm going to tell you what a picture where 2 of them are there. Right. Okay, so what is it going to be? It's going to be a new tensor. So I'm going to imagine the blue. Imagine the blue is one single blob that I kind of shrink together. And I've got now, instead of 5 edges or 3 edges coming out of that one single blob, I now have 8 edges, right? These 5 and these 3. And to tell you what the number, so with tensors, this is going to be a new tensor. With tensors, as soon as I label the edges around the outside, out should pop a number. I'm going to tell you what number I'm going to pop out. So you label the edges around the outside, okay? And then I'm telling you what number. What is the number? Well, each of these different m's have been fully labeled, so they each have a number to it associated to them. And the number I associate with this together is the product of those 2 numbers. Okay, so now I can take tensors and I can put them, if I have individual ones, I can stick them on the same picture. And I have a new tensor out of that on a bigger space. Or if I want to think of it as a vector, this is now a vector on 8 copies of H. So that's the first thing I can do with it. And the second thing I can do is contract, which is to say, once I have 2 nodes, I can join one of the edges to one of the other edges. Right? And I want an interpretation of that picture. Right? So first of all, it's going to be a new tensor with the number of edges corresponding to the number of free edges here. Right? So again, I'm going to sort of imagine that I put a red dotted line around everything, and I sort of contracted that red dotted line into this little thing. And so I have to tell you now, if I label everything around the outside here, what the number I associate with this is. Okay? So I label everything around the outside. Okay? Now this guy is not labeled, right? Because he wasn't on the outside. Right? So I'm going to sum over all possible labelings of this guy. So for any possible labeling of this, now I've got a picture where everything's labeled. So for any possible labeling of this, all these are labeled. So for any possible labeling of this, I have a number here, a number here. I multiply those two numbers together. And then I sum over all possible labelings. So, okay, so this is maybe a lot of mumbo jumbo. It maybe doesn't, it's hard to absorb very quickly if you haven't seen it. But let me just give you a sort of feel for what it's telling you, and maybe you can do that yourself, which is I'm going to draw some pictures, and we're going to associate these things to regular algebraic things that we often do. All right, so M and P, I ignore the sort of I on the side. So M and P, right, were two tensors which I joined along an edge. Okay. If I think about what that means, right, it's the sum over that labeling I of Mi times Pi. And what is that? That's the inner product. If I thought of M and P as vectors, what I've written down there is now a number. And the number turns out to be the inner product of M and P. And this is the point where you say, well, shouldn't there be a conjugate? And I say, don't worry about the conjugates. Just think of everything as real for the moment. Okay. And here's another example where M was a bigger tensor and P was a bigger tensor. But if I think of both of those bigger tensors as vectors, then this picture is the inner product. Okay. Now I'm going to draw a second picture. Here's a second picture of a combination of an M and a P. And in this case, M, right, was sort of a vector with two things coming out of it. And I'm going to think of that M as a linear map from the top edge to the bottom edge. So it's a matrix. Okay? And P is going to be a linear map from here to here. And if I actually do the calculation of what this ends up being, this ends up being matrix product. Right? So here's a picture, honest to God, matrix product. There's nothing, it's not, it really is the matrix product. You sum over J of Mij times Pjk. That's what you get out of it. And traces this picture. So if I have a matrix M, if it's a tensor M, but I think of it as a matrix from here to here, if I loop them around back to themselves and I compute what it comes out of this, this is a sum over the labelings. This is a label I. This guy gets labeled by Mii. This is the sum of the diagonals. This is the trace. Okay, so now we're sort of fully ensconced. We're ready to go. And let me just have some minor adjustments. The first minor adjustment is, before I told you that every edge has the same labeling set, now I'm going to tell you we're going to allow edges to have different labeling sets. And I'll just make sure when I join two edges, the edges that I am joining have the same labeling set. So that corresponds to having some Hilbert spaces be different sizes than other Hilbert spaces. And the second thing I'm going to do is, instead of using dots, I'm going to use boxes, because boxes often are familiar to people who do circuits. And so a circuit is a matrix, and so we can think of it, there are many different ways to think of this matrix, or this tensor, as I've said, but we can think of it as a map from here to here. Right? And so now let's take a look at the coin flipping network and what it looks like. So what I do is Alice and Bob first start out with an initialized state. Right? So what is their initialized state? Well, I can write it as a tensor like that. That's a vector. Right? So here are two vectors, one on Alice's side, one on Bob's side. Bob applies some unitary gate, right? And then sends part of its operating space over to Alice, right? Or maybe you think of this as the channel that they're communicating on, right? And then Alice applies something, right? And sends their thing back over to Bob. Bob applies something. We continue this for a while, right? And in the end, so maybe there are a bunch of more different things in the end. Okay, and here's sort of a distinction to make. In the end, we make a measurement. And let's write down the chance that both people measure heads. Okay, both people's outcome measures heads. So what does that mean? That means that actually what happened here was a projection onto the projective part of the measurement that was heads. So this is a projection operator, and this is a projection operator. And what we have left is this decomposition of this is the vector, right? That would be in the subspace that for which the outcome just before you do the measurement was going to be a head, right? Okay, so here, this is a vector. So let's take a look at this. This is a vector. Where does it sit? Well, it's, there are a lot of closed edges here. These are the only 3 open edges, right? So it's a state. It's a vector. We'll think of it as a vector right now. Okay? And the vector that it is the component upon which, heads is going to be the outcome. So the probability of getting heads is exactly the norm squared of this vector. Okay? So here's a vector. The norm squared of this vector is the probability of getting heads. So how do I get the norm squared out of a vector? Well, what do? I inner product it with itself. Right? That's how I get the norm squared. I have a picture for inner producting with itself. What do I have to do? I just have to join this guy to itself. I have to put a second copy of it and stick it together, just like inner product. Right? So I do that by flipping it over and joining it to itself. And now there's sort of a small subtlety, which is if I was to, these B's have turned upside down, which means they're the U stars. Okay? And so you're familiar with this. A lot of you are familiar with this in other ways. But here's the picture. This is a number, right? Honest to God number. What does it represent? It represents the probability of the protocol coming out heads. All right. So here's now the point. Take that and isolate the stuff that Bob can do and the stuff that Alice can do. The blue separates what Alice has complete control over what they're doing on that side. Bob has complete control over doing what's on the other side. And the constraints they have is they have to play unitaries or partial isometries in here. And they have to play a projection in there. And now, if you take Alice's part and separate it, and Bob's part and separate it, how can I interpret this picture differently from how I was picturing it before? The left side is some tensor. Right? The right side is some tensor, and we're gluing them together, which is inner product. Okay? So what we can see this is a game where Alice picks from their choice of vectors, Bob picks from their choice of vectors, and they play their inner product. That's the outcome of the game. So remember what our plan was, right? Our plan was to show that Alice's set of strategies somehow sits in some convex set, right? And that Bob's strategies are the dual, and then we're in a duality game, as it was called, and we're done. So how do we do that? Well, we just take this blue picture, okay? And what I'm going to do is, what goes on here, the mirror of it is coming down here, right? And so I'm just going to bend these two pieces to the side just to look at them in a different way. And what I'm going to look at them as a map from these input edges, the guys on the top, to the output edges on the bottom. So that becomes this picture here. Okay, so does everybody see sort of, if you take the blue and you sort of stretch it back out that way, you had what you had before. But now I'm really thinking of it as a map from the top to the bottom. It's clearly a matrix. I mean, I'm thinking of it as a matrix. It's positive because there's a correspondence between these guys, and you can sort of realize it. You realize, if you think about it for a minute, that it's something times its star that you're multiplying by. So all of these are positive. And similarly for Bob, I did the same thing. I took Bob's thing. Let's see, what did I do exactly to it? I guess I took the bottom part and I sort of bended it upwards, and I took the top part and slid it around downwards. Right? And so to get the actual, so another way to glue these things together is to multiply these two matrices together, joining them up there, and then taking the trace, which, what does taking the trace means? It means joining this guy around to that guy and the rest of the guys. And if you sort of follow that through, you'll see you get right back to this picture. Okay, so what's true of these collections? So now we've isolated the spaces on which Alice and Bob can play, and what's the set of strategies? Well, as matrices I mentioned, they're positive. They contain 0. You can sort of see that pretty clearly by just sticking in a projection 0 here to make the whole thing 0. They're convex. That's not very hard to show, but doesn't allow you to have lunch in as much time as you would otherwise, but it's pretty short. And the thing that is very cool is the fact that these are dual spaces. And this is the Wachter-Skotowski is sort of how they showed that these two spaces were dual. And it's a sort of nice inductive argument. It's, when you strip down all the pieces, it's really sort of quite pleasant.
The hard part is definitely this inner product is always less than or equal to 1.
Right.
But the hard part is showing that everything's achievable.
Yeah. Exactly. Okay. And so we have our duality game. All right? So now we go back to our duality argument, and we're done. Okay. So now, the thing is, when I agreed to give this, when it was organized to give this talk, I had the dream that this would be a better presentation than it is, because there's certain things that are missing. And these are the best things that are missing. These are the biggest pieces that are missing, right? How do we see the best play for Alice given Bob's play in pictures? Okay, so, sorry, there. Okay. So imagine fixing Bob, right? There's some best play for Alice. It shouldn't be that hard to see what it is, but I don't know what it is. And the second is even sort of an even easier question, which is, remember how that duality, the original duality argument was very simple. It didn't require, here, okay? Everything up, we didn't require full duality, right? All we required was, here's B0, which is where we're starting. We just need to guarantee that this guy is in B. Right? And how do we do it? We use duality to do it. We said, hey, look, this guy doesn't do so badly, so. But really, it's just a scaled version of the old guy, right? So it shouldn't require you to just have to put this big hammer on to say that you need duality. You should be able to see that this scaled up version is still a valid play for Bob. And that was the thing that sort of kept me not preparing the talk, because I thought as soon as I get that, I could make a talk that lasted 10 minutes and we could get out of here. So that's sort of a really open question that I would like to know the answer to. And maybe over lunch somebody can do it. So, and I'll stop there.
In the interest of lunch, let's have one question.
It seems that you are not using much of the structure of coin flipping. So should you apply this to any bipartite protocol? Essentially, it's the same type of tricks. I mean, I don't see why coin flipping was crucial here.
No, I don't. I don't either. That's part of the reason why I wanted to sort of put it out there. Is the thing. Now, if you wanted a protocol where there was, I guess one comment to make is if you want to view a protocol where people could start with some entanglement before you start, right? That actually just changes the picture by saying instead of starting with product states, you can start with something entangled, which you can just sort of depict by a line going from one to other and sticking a tensor up top. But I think all these, I really do think that thinking about it this way is helpful.
So it is more general, and John and Gus have a paper that doesn't do the tensor network picture, which is really what Zeph came up with, but they phrase it algebraically, this duality, and that holds for, I mean, they have a very general statement there.
Okay, let's take Zeph again. Are we having another question? Let's have one more little question.
So this could be, but is it clear why it doesn't work for weak coin flipping, for example? Like what goes wrong?
Yeah, so the duality game relied that both people were pushing in the same direction.
I see. So it's again.
Right, so you're sort of just saying, look, one person wants heads and the other person is willing to give them heads. So it's really it's plugging it into the duality game that doesn't.